everybody. In this video, I want to take a look at a more modern quantum mechanical description of how atoms are structured. And that solution comes from what's called the Schrodinger equation, or the Schrodinger equation. So down here is a picture of Erwin Schrodinger, who was an Austrian scientist and proposed this method of understanding the atom. And yeah, that is me next to Schrodinger. He taught in Vienna for a few years. He was Austrian, like I said. And so they have a bust of him in the courtyard at the University of Vienna. I lived there for a little while, and so it was exciting to me as a chemistry major to go and see the busts of all the people who worked on really cool science things that I saw in my classes. Why, yes, I am a nerd, I know. So this modern description of the atom, sometimes just called the quantum mechanical description, Schrodinger said that light has particle properties, so something that's a wave has particle properties. And so electrons, which we used to think of as particles, probably have wave properties. And so he said, well, we can describe waves. We can describe sound waves and water waves. So I bet you there's an equation for quantum mechanical waves, for electron waves. And a lot of math and a lot of theory later, there is one. It applies to a lot of different situations, and if you want to become a chemistry major and take P-Chem with me, we'll talk about this equation all the time. It is so cool what you can learn from it and what you can do with it. But the situation that we're going to focus on here is the atom structure. And the terms that I want you to know are a wave function, and this letter is called psi in Greek. And what a wave function is it's a description of, and I'm going to say position in quotation marks because that's not true, but it's close enough for the purposes that we're doing here. What's really important is the idea of psi squared, and it's a probability of position. Remember how I said that one of the precepts, one of the tenets of quantum mechanics is that we can't think about position in a specific deterministic way. The electron is not here or here. There's a probability of it being in a certain area. And psi squared, which comes out of Schrodinger's equation, describes that probability. And psi squared really just looks like a map. So you notice how this is kind of a sphere and each of these dots is here, and you notice that the dots get less dense the further away you move from the center. That's what this R is about, and that's what we're plotting here. Right? We're plotting the probability of finding an electron, which goes down the farther away you get. That ought to make sense from our Coulomb's law stuff earlier. Remember in Coulomb's law, the farther away an electron was, the less attracted it was. So Schrodinger's equation matches with that. Sometimes we do a radial probability. So what we say is, oh, there's a sphere with this radius, and that's the probability of finding it. You also spike up and then back down. We'll talk more about that shape later, but that just means that there's this three-dimensional volume that we're looking for the electron in. This is a particular point in space. This is a particular volume. Lastly, what we really draw for ourselves is we take this information and we turn it into a map. And you guys are familiar with contour maps. So things like you've got the lines that are closer together and farther apart, and maybe that represents a hill on a map of the world, for example. That's kind of what we're doing with the electron. And so they look like spheres or dumbbells or clover leaves, and that's something that describes 90% probability of the electron being present there. Don't worry too much about that, but these shapes, remember, just again, they're not a certain position of the electron, they're a probability map of where it could be. And that helps us actually learn quite a bit. The other thing that comes out of Schrodinger's equation is the idea of quantized energy. And by the way, the Rydberg equation fits here. So you don't have to do anything new here. You can basically use information from the Rydberg equation and a couple of tweaks for higher order atoms to make this work. Quantum numbers are how we describe these wave functions. So remember, a wave function is a psi, and a psi has 4 quantum numbers associated with it. N, L, I'm going to make my L's cursive, M sub L, and M sub S. And those 4 numbers together, actually really 3 of them, help describe how I got something that was shaped like a sphere, something that was shaped like a dumbbell. And remember, they're pointing in 3 different directions, right? There's up to down, there's side to side, and there's in and out. So there's 3 different orientations of a dumbbell. N, L, and M sub L describe that. Or you notice that there's these 4 of them look like clover leaves that are tilted different directions. 1 of them looks like a dumbbell with a donut around its waist. Those are a different set of N, L, and M sub L quantum numbers. And so the name for these, again, just like Bohr's model, we call these quantum numbers. And they describe how we get all these shapes. N describes what we'll call size, and its name is the principal quantum number. L, and again, I make it like a cursive L as much as I can. L describes the shape. M sub L describes the orientation. And the name for this one is the magnetic quantum number. And then M sub S describes something called the spin. These 3 are what go to this map up here. This one is kind of a separate quantum number. But all of them together, when we work together with them, are going to build the periodic table from the ground up, which is a really cool thing. Mendeleev actually built the periodic table on masses, and quantum mechanics is going to build it on electrons. And so we get the same thing coming from 2 different directions, and that's a really fun thing for scientists to find out. So again, that principal quantum number is called N. It's also sometimes called the shell quantum number. N could be any number starting with 1, right? N can be any number 1 or larger, and it has to be an integer. And it describes size. If N is up, size is up. That's the only thing you need to know. We start at 1 and we work our way out. And by the way, this is the same one that showed up in the Bohr model. But as long as N is 1 or bigger, we're cool. The next the next quantum number is called the angular momentum quantum number, or L. And sometimes a book will call this the subshell quantum number. L can start at 0. So the smallest L you can have is 0. It could be or 1 or 2, all the way up to N minus 1. That's actually really important. There are options, right? There's lots of options. What it describes is the shape. And you notice on the left, we have letters for different L's. So S is L equals 0, P is L equals 1, D is 2. And you notice that the larger the L gets, the more complicated the shape gets. Perfectly fine, right? And what we're representing it by is just this little letter L, and again, saying something about the complicatedness of the shape. Next quantum number, the magnetic quantum number, M sub L can actually have negative values. This is the first one that can take on negative values. It can go all the way from L up to and through 0 and all the way up to positive L. So for example, if L equaled 3, M sub L could be -3, -2, -1, 0, 1, 2, or 3, right? They are all options. What it's describing is orientation. And here's the thing to think about. An s orbital is L equals 0. So your M sub L options go from -0 all the way up to +0. You're very limited, right? And an s orbital is sphere-shaped. You can't turn a sphere in any other direction and change how it looks, right? So we only have one orientation. That's why we only have one M sub L quantum number. Moving on, M sub L, right? This is an L equals 1, a p orbital. So m sub L could be -1, 0, or +1, okay? A p orbital is a dumbbell shape. A dumbbell looks different to you if it's pointing up and down, if it's pointing side to side, or if it's pointing in and out. There are 3 distinct ways to orient it. That's why I have these. These are all possible descriptions of an electron in an atom. D orbitals, and let me make some erasure here for you. D orbitals have even more options, right? A D orbital is L equals 2. So we've got -2, -1, 0, +1, or +2. Look, there's 5 of them. Keep in your head that these are all possible ways of describing an electron in an atom. They're all available to electrons. And so there's all these spaces for electrons to occupy. Those start piling up and compounding, and that's how we're going to get to the periodic table in just a second. Lastly, we need a quantum number called spin, or m sub s. And the reason we found out we needed it was we shot atoms, hydrogen atoms, through a magnetic field, and we found that they split into 2 components. And so that couldn't have been because they were S, because S is our sphere. So there must be this other magnetic thing that goes on. It turns out it's only necessary for certain things that have unpaired, well, I'm not even going to say that. It's only necessary for multi-electron atoms. Let's go with that. But m sub s is called a spin quantum number. It has 2 options, +1/2 or -1/2. Both are equally valid, and we don't care aside from it being +1/2 or -1/2. Putting all of those quantum numbers together, n, l, m sub l, and m sub s, helps us rebuild the periodic table. And the way that we think about that is by building ourselves a table. We work our way from n to l to m sub l to m sub s. Because an electron is described by n, l, ml, ms. So a combination. An atom or an electron could have 1, 0, 0, 1/2. It could have 2, 0, 0, -1/2, right? There are all these possible quantum numbers, and every possible set of quantum numbers is an electron, represents an electron. One thing that we need to know is that if I'm looking at the same atom, it's called the Pauli exclusion principle. So Wolfgang Pauli was the Swiss scientist that proposed this. And he said that if I'm looking at the same atom, all the electrons in helium or all the electrons in sodium, I can't have the same set of quantum numbers for any 2 electrons in that atom. So that matters because when I run out of quantum numbers, I have to add another shell. So over here in n equals 1, if n equals 1, based on our rules, L could equal 0, and m sub L has to equal 0, and then m sub s could be 1/2 or -1/2. So that means that the n equals 1 shell has 2 slots. Similarly, in n equals 2, I could have L equals 0. That's an acceptable option with the way that n and L are related. Or I could have L equals 1. And the s orbital has m sub L equals 0. The p orbital has m sub L equals -1, 0, or +1. And then each of those has a 1/2 or a -1/2 associated with it. So what I can say is that, you know, there's 2 options in m sub s, and then there's either 1 or 3, right? 1 orientation for the s, 3 orientations for the p orbital. So there's 8 electrons that can fit in the next shell. So on and so forth. 2 times 1 plus 3 plus 5, so 2 times 9 equals 18. And then 2 times 1 plus 3 plus 5 plus 7 is 16. So there's 32 electrons that can fit in a shell. That is so cool, and I can't underestimate this for you. Let's take a look at the periodic table in just a moment. Right? Any orbital holds up to 2 electrons. because of m sub s. And that's how we get this pattern of 2 times 1 or 2 times 1 plus 3, etc. Going forward then, what I want to think about is that going across, that was not what I meant. Going across the periodic table, we are filling an n. Going down the periodic table, we are adding n. So this row is the n equals 1 quantum number row, and n equals 2, 3, 4, 5, 6, 7, right? And what did we say? We said that shell n of 1 could fit 2 electrons. The first row has 2 elements in it. The second shell, we said, could fit 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. When we run out of electron spaces in a shell, we have to go on. What do you think? There's probably going to be 18 elements across the third shell. Here's the funny part, and this will come up later. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And last but not least, the complicated one, and I'm going to have to erase to make some room, is that 4 could take on 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I miscounted because I counted too many. I should have been a little bit further along. I promise you it works out to 32. That fourth shell will hold it. What happens is I should have skipped back to here instead of back to where I skipped. Let's try this again. The fourth shell can hold 32, and this is where it gets fun. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Like magic, it all comes back. It's actually not magic, it's quantum mechanics, and it's how those numbers fit together. So we can actually build the periodic table on quantum numbers alone. And that is just one of the coolest things that I can think of. In future videos, we're going to practice the interrelationships between these quantum numbers, and we're also going to talk a little bit about why all of this funny skipping happens. So for now, just take me on faith, and I'll fix it for you in a little bit so that it all makes sense. See you then.